Hey guys, so this is a presentation on how to read well logs, or as I like to call it, log reading for dummies. I'm gonna take my camera out so it doesn't get in front of the slides and see how this goes. Okay. Um, so first things when reading logs is to figure out what's your scale. We have two types of scale. Um, we have linear scale, and logarithmic. We have usually three tracks, and the the way we're gonna see it in this course is three tracks, with the first one being linear for SP and gamma ray. The second one is logarithmic for the resistivity, and the third one is the linear for porosity. So how to read the logarithmic scale? For the resistivity, we usually see it going from 0.2 to 2000. So if it starts with 0.2, then the next one will be 0.3, then 0.4, 0.5, and so on till we reach 1. And then when we reach 1, next one will be 2, 3, 4, 5 till 10. And then from 10, 20, 30, 40, 50, 60, 200, and then 200, 300, 400 to 1000, and finally the last one is 2000. So I've seen some of you guys struggling with this. It's not that simple to read at first, but once you get uh, the hang of it, it's easy to read. So if we have like a log on this between these two lines, we would have like a reading of 35 to 36, because it's between 30 and 40. So basically any reading that you throw, if you have a average line going between two, is acceptable. So just try to figure out what in which line you are when reading the logarithmic log. Spontaneous potential. Um, the way Amir told us how to read it is to get the scale that you have. In this case, we have from minus 160 to 40. So that gives us a difference of 200 millivolts. So 200 divided by 10 subdivisions, which are the subdivisions we have here. It's 20 millivolts each subdivision. So for the SP especially, we pick the center line and we do it as 0. So everything left from the center line will be minus, and everything right of the center line will be plus. So in this case, we have this um, this uh, cleaner, which would be not cleaner, sorry. This lower reading, which would be like approximately 42 millivolts, and the higher reading here would be 76 millivolts. Okay, and this is something that Amir told us that might show up in the test. he might ask us to draw a sketch of the responses of the SP log. So basically, the higher the difference between the resistivity of the mud and the resistivity of the water in the reservoir, the the higher the difference we will see, the higher the response we will see in the SP log. So if we have the resistivity of the mud equals to the resistivity of the water in the reservoir, we will have no response whatsoever. If it's the resistivity of the mud is a little higher than the resistivity of the water, we're gonna have a small response. If it's very higher, if it's too high in relation to the resistivity of the water, then the response will be higher. Actually, sorry, lower in this case because we are going for minus here. And if the resistivity of the water on the reservoir is higher than the resistivity of the mud, then we will have a higher response. We have a positive displacement on the SP. Okay, gamma ray. Gamma ray reading is straightforward. We go from, in this case, from 0 to 150. And so we have 150 API in the scale divided by 10 subdivisions. So 15 API in each subdivision. So starting from the left, we have 0, 15, 30, 45, 60, and so on. So in this case, this reading, which would be in our case the clean sand, the lower the gamma ray, the cleaner the reservoir is. So for the clean sand in this case, we would have 85 API, and for the shale response, which is the highest peak in gamma ray, we have 120 API. So for the shale, we can have two approaches. We can either select a average of the shale if it's not varying that much, or we can get the highest peak on the gamma ray. I've seen in Amir's lecture material that he did the highest point. The way I used to do it in the industry was using average. But yeah, we might be, either way we might be okay. I think if we can argue with him. But I would use the way he taught us on the lecture, which would be the highest peak, unless it goes out of the scale. Okay, if it goes more than 150 API, then I would do an average. So for porosity logs, sonic density, and neutron, the scale it's something that we need to pay attention, because we might have, as we have seen, minus 15 to 45 percent porosity, or in this case we have from minus 10 to 30% porosity. So the zero will be somewhere inside the scale. Okay, so in this case we have from minus 10 to 30, so it's 40%, and we have 20 subdivisions. So for each subdivision, we would have 2%. So from going from here to from minus 10, so we have minus 8, minus 6, minus 4, minus 2, and then 0. Okay. What we need to focus when we have this situation is that if, for example, this was our reservoir, we would have a negative uh, response for the density porosity, which means that this log was compensated for another lithology. So the way we read it is we mark a average of this line, okay? And it's the same for the neutron porosity, which in this case is the solid line. So we would have an average of this line. If it was like in here, for example, this would give us 2% porosity. Okay, actually minus 2% porosity because it's right from the zero. So if we have a negative porosity, we just flip it and make it positive. And then for the porosity that we use for the calculation of the formation factor, we would do an average of density porosity and neutron porosity. Okay. Other way to that we can get these um, logs is in a scale of decimals, not percentage, but it's still uh, we still rate it as percentage. In this case, we are going from 0 to 60%. There is no negative porosity here, so it's the rating is straightforward. Okay. In this case, we have 60 percent and 20 subdivisions, so each subdivision would be 3%. So in this case, going from 0, we have 3, 6, 9, 12, 15, and so on. So same thing, do an average of the line inside your interval of interest and read that average, and that's your porosity. Now the resistivity, because it's a logarithmic scale, it's a bit harder to read. This is the schematic that Amir gave us. We are just interested in the reading of the resistivity in the uninvaded zone, in the virgin zone. So that's our RT, and the resistivity of the water in that zone, which is our RW, and RW is given. Amir will give it to us, so the only thing we need to read is RT, and how we do that. RT is we get it doing again an average of the curve inside an interval. Okay. In this case, our deep resistivity is this one, AITH 90. Usually, actually, Amir might he won't give us these logs in particular because these ones are hard to know which one are the shallowest and which one are the deepest. So he would give us something like ILD or any other mnemonic is what we call the names of the logs as mnemonic. So any other mnemonic which has a D in it, that's the curve you need to read. That's the deep curve, which will read the, let me go back to the previous one. If I can do that. No, I can't. Sorry. So, so to read the uninvaded zone, we use the deep resistivity. Okay. And let me see. Oh, I got AITH again. Okay. So if our zone of interest is this zone with gas, I'm gonna talk about gas effect in a bit. But if our zone of interest is this, then our average would be somewhere around here. And this scale is going from 0.2 to 2000. Okay, so this is 0.2, this is 2, this is 20, and this is 2000, 200, sorry, not 2000, 200. So our average would be somewhere around here. This is 20. No, sorry, 2. This is 2, 3, 4, 5, maybe between 5 and 6. I would go with 6. Okay. So this would be 6 ohm meter, which is the um, unit for resistivity. And then we would use that in the formula for SW, which is square root of the formation factor times the resistivity of the water divided by the resistivity that we'll read on the log. Okay. Now for gas effect. Um, Gas effect occurs when we have a big separation between the neutron porosity and the density curves, because the density will read the rock with gas as having less density, well, for obvious reasons, and neutron porosity will read uh, less free hydrogens in that same rock. So the neutron porosity will give us a low porosity reading when we have gas, and the density will also give us a low density reading. So as the scale for the neutron porosity is flipped, we're going to have a big separation between those two curves. Okay. And also, and we can't see it in this case because it not always shows on the resistivity, but we have a higher resistivity when we have gas than when we have oil. Usually we see the response for the resistivity for the gas going over the scale of the resistivity. So it would be uh, far away from the the right edge here in the resistivity scale. Okay, so uh, one thing that I uh, wanted to talk to you about resistivity is that the lower the resistivity, um, the higher chance we have to being on brine. If we have fresh water would give us a similar response to oil in resistivity. Okay, so we need to be aware of that. I don't think a mirror would give us um, a well with fresh water and oil, because that would be uh, you know that would be bad for us. It's hard to say just looking at the resistivity if we are on the oil or the freshwater zone. So um, if we have an oil contact like this, it's because the water is brine, is salt water with the higher the separation, the higher the concentration of salt in the water. Okay. You can see that in a clean reservoir, um, the response for resistivity is even lower when we have brine than in the shale. The shale is what we call the water baseline, and if the reservoir is good and we have brine, the response for the water will be even lower than the shale. Okay, and we can see that in this log that I showed you before to so we could make the readings for the resistivity. We have the neutron porosity log, which is this one, dashed one, and we have the density porosity log, which is the solid line one. So when we have gas, they separate. The density for the reservoir with gas will go low. We're gonna have a reading. Actually, if we have, sorry about that. In that other example, the density was in density, so it would give us a low reading. But since this is in porosity, the porosity for the density will go high. Okay, so the porosity for the density will go very high, and the porosity for the neutron will go very low. So that's how we know we are in a gas reservoir. That there is a big separation between those curves, and yeah, that's the gas effect. Okay, that's it for now. Um, I might cover some other things in another video. If you ask me questions, I will be happy to um, cover other things in another video, or just give the answers on our group on WhatsApp. But for now, that's it. Yeah, see you around.